Okay, Spartan fans, we're going to start with chapter 3 now, the derivative. The derivative is the basis for all of calculus. And essentially, calculus is just a lot of fancy algebra. So let's start with the limit as h approaches 0 of the f of x plus h minus the f of x all over h. And this represents the slope of a tangent line at any point on a function. This is the slope of a tangent line at any point along a function. Okay, well, if I know the specific point on the function, so let's just call that a, and you're going to see x equals a lot. At x equals a, it's going to be the limit as h approaches a of the f of a plus h minus the f of a all over h. This is generically for any point along the any line, tangent line along the curve, and this is for a specific point of the tangent on a curve. Okay, so if this limit exists, so if this exists, then the tangent line at that point exists. Well, guess what? This is a derivative. The derivative is just a fancy name for the slope of a tangent line at a specific point on a graph. And the derivative, you're going to hear it called the f prime of x. Okay, the f prime of x. And the f prime of x is simply the limit as h approaches 0 of the f of x plus h minus the f of x all over h. And this is the definition of a derivative, mathematical definition of a derivative. But all this is the slope of a tangent line at a specific point. Okay. Let's say that point is a. All right, well, you have some function. The point is x, f of x, and you have another point, a, f of a. How do you find the slope between these 2 points? So we would say the limit as x approaches a. How do you find slope? F of x minus f of a all over x minus a. This is another way to find the slope. So if you've got x and x plus h, and then you plug in and we realize that you end up getting only h remaining in the denominator. So instead of using x plus h, we could use a, and this is just a fancy formula for slope. There are a lot of different notations for the f prime of x. So on your book, in your book on page 97, let me zoom in here. Okay. These are all different ways to denote the derivative of a function. F prime of x is the most common. You will see these other versions, and we'll talk about those more. Dy dx and df dx are another way to talk about a derivative of a function. It's all about notation. It's all about notation. We are going to use primarily right now the f prime of x. Okay, so let me zoom out here and let's do a couple examples. Let's go back to right hand and left hand limits for a minute. So if you have the limit as x approaches a from the left of some function, and that equals the limit as x approaches a from the right of the function, what do we say about the limit? Okay, we say the limit exists. So if the left hand equals the right hand, then we say the limit exists. Well, if the limit exists, then we know that the tangent line exists. So if the limit exists, which is right here, then we know that there exists a tangent line. So, and tangent line exists at x equals a. And we say that the function is differentiable at a. The left hand and the right hand are the same, therefore the limit exists. And if the limit exists, the tangent line exists at a, right? Because the limit as x approaches a, h approaches a, whatever, this is the slope of the tangent line. So if the limit exists, the tangent line exists because you've just found its slope, and therefore we say that the function is differentiable. So let's look at an example of a function, and I'm going to find the derivative using the f of x minus the f of a all over x minus a. The limit as x approaches a of the f of x minus the f of a all over x minus a. And we're going to find it using the definition of the limit as h approaches a of the f of a plus h minus the f of a all over h. So this, oh, it's a, whatever, a, x, who cares? So these should be the same. One is a formula for slope. One is a formula for slope using h as opposed to using x. Okay, so here we go. Let's look at how about the function is x cubed plus x. And let's say at a equals 1. Polynomial function, degree is 3, and behavior is down, up, etc. That's a 3. Okay, so let's figure out what the f of a is. So the f of a is the same as the f of 1, which in this case is 2. All right, so let's start with part A. All these A's gets confusing. So I'm going to want the limit as x approaches a is 1 of the f of x, which is x cubed plus x, minus the f of a, and the f of a is 2, all over x minus a. Ooh, I would love to do a straight plug-in. It's not going to help me, right? Because if I do a straight plug-in, I'm going to get 0 in the denominator. So I'm going to cheat. Yes, you heard correctly. I'm going to cheat. I've said before that this denominator of x minus 1, it's got to reduce out. It has to reduce out. Otherwise, I won't be able to find the limit. And the fact that this is a polynomial function, I know it's a smooth curve. I know it's continuous everywhere. So the limit is going to exist at every point along the curve. So I'm going to use the fact that I want the x minus 1 to reduce out. So if I want the x minus 1 to reduce out, I have to have a factor of x minus 1 in the numerator. So that means there's got to be something left. So if you remember your p over q, this means that 1 needs to be a 0 of the function. So I'm going to do some synthetic division. 1, 0, 1, negative 2. It's 1, 1, 1, 1, lots of ones, 2, 2, 0. So x minus 1 is indeed a factor of x cubed plus x minus 2. And I'm left with x squared plus x minus 2. The 0 comes from 0x squared. There's a missing term, so you need to put a 0 in as a placeholder. And indeed, bada bing, bada boom. This is the limit as x approaches 1 of x squared plus x minus 2. Just a refresher, if you go straight from this step to the answer, you're going to lose points. You need to show the remaining function after you reduce. And now, when you plug in 1, that's 1, you get 0. This means the slope of the tangent line is 0. That means that at the point 1, 2, it's a horizontal tangent line. 0 slope, horizontal. Okay, well, when I do this same problem using the other definition of the derivative, should get the same answer. Let's give it a whirl. Okay, so the f of a plus h, this is going to take some time. So this is the limit as h approaches 1. A plus h is going to be a plus h cubed plus a plus h. Minus the f of a, which is 2, all over h. And two things. This should be the limit as h approaches 0. And I know that a is 1. So I'm going to, I should have done that from the beginning, but I didn't. We'll do it now. So this is going to be a is 1. So 1 plus h cubed plus 1 plus h minus 2 all over h. So clearly this is a problem. I can't plug in 0. Okay, hopefully that's a bit easier to see. So Pascal's triangle, when you multiply out 1 plus h cubed, that is going to be h cubed plus 3h squared plus 3h plus 1. Pascal's triangle, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. You know these things, it's going to save you a lot of time. Plus h plus 1 minus 2. Okay, 1 plus 1 minus 2 is 0. And we have 3h plus h, which is 4h. So when you factor and you reduce, you should get h squared plus 3h plus 4. So the limit as h approaches 0 is 4. And this is not good. They are supposed to be the same. So let's go back. These need to be the same. You're just doing alternate definitions of the derivative. So we should be getting the same answer. It's kind of like point slope form, standard form, slope intercept form. They're all the same. And my mistake here is that it is x squared plus x plus 2. So this should be plus 2, which is indeed 4, and they are the same. So it doesn't matter which definition you use, the derivative at the point, the derivative of this function. So we say the f prime of, we were finding 1, is equal to 0. Four, not 0, 4. This should be a 4. Okay. Let's take a minute to find the slope of the curve at any point. So what we did here was we found the slope of the curve at a equals 1. Let's find the slope of the curve at any point. So let's find the derivative of the function at any point. At any point x equal to a. Limit as h approaches 0 of the f of x plus h minus the f of x all over h. Or you could use the limit as h approaches x. I always get the x's and the h's backwards. The limit as x approaches a of the f of x minus the f of a all over x minus a, and we're going to use the function x cubed plus x. So if you remember at the beginning of the video, I said that calculus was just a bunch of fancy algebra. It is. Pick one of them, go for it. So you'll notice, zoom this in a little bit. I used the definition of the derivative at a point. This is instantaneous velocity, by the way, in case you've forgotten. And I did all the math and I got 3x squared plus 1. Great. And you'll notice that in the above example where I said, okay, a is 1. We got 4. And if a is 1, you do indeed get 4. And I started this one, I was like, oh my gosh, I don't know how I'm going to factor this and how am I going to do synthetic division. Now, I don't quite know how this is going to work because when you synthetic divide, remember that the order in which the numbers come in, that matters. And this doesn't work. And the reason why this second definition, this is the slope of a line at a specific point A. This is the slope of a line at a specific point A. I don't know what specific point. Therefore, I could not use the definition with plugging in a point using x is equal to some value a. And if you're thinking, well, wait a minute, I know the specific point is a. A is not a specific point. And when you plug it in, of course, you get 0 in the denominator. So this does not work. I need a value for A. Let's look at a root function, rationalizing. Some of these look a little bit funky when you try to rationalize them. Again, this is a bunch of algebra. So let's find the slope. At x equals 4, given the f of x is equal to root x. Okay, so we got two options here. We have f prime of x is equal to the limit as h approaches 0 of the f of x plus h minus the f of x all over h. And then we also have the f prime of x is equal to the limit as x approaches a of the f of x minus the f of a all over x minus a. And this definition of the derivative will work because I have a specific point. So in this case, if x is 4, the f of 4 is 2. Okay, so I'm going to get started. You can finish it or go back if you are a little bit confused where I got some of these answers. Square root of x plus h minus the f of x, which is the square root of x, all over h. And I know x is 4. Why do I always forget to plug that in? Because you guys aren't here to help me. And I also know that the f of x is 2. Of minus positive 2, not from the left. Really need to be using my erasable pens. Okay. All right, I think I've got it. I'm just going to rewrite it. That's better. Wow, what do I do from here? What do I do from here? Because I can't just plug in h is 0. That doesn't work. Nothing reduces. So we are going to, lack of a better word, we are going to reverse rationalize. So I'm going to multiply numerator and denominator by root 4 plus h plus 2 over root 4 plus h plus 2. This is 1. So it's like we're kind of rationalizing the numerator, but what I need is I need an h in the numerator to reduce out with the h in the denominator. Finish it off. Hopefully I didn't make any mistakes. You have a square root in the denominator and you're always taught to rationalize. Well, in this case, like this is not my final expression. So I wouldn't leave, if I was just doing a problem like this, I would rationalize it, but I'm doing a limit and I'm evaluating and I get 1/4. Fancy schmancy math. Okay, so now when I find the limit as x approaches a, which in this case is 4. The f of x is root 2. The f of x is root x. I can't wait to go back to the whiteboard days. The f of x is root x minus the f of a, which is 2, all over x minus a, which is 4. This is confusing, I think. X is 4, and then we're approaching 4. So what you might want to do is change this to a to help yourself out. That might make things a lot easier. You're going to see it written in the book, most books, I think, as x equals a value. And so if it's going to help you when you do the substituting, you might want to call it a as opposed to x. All right, so same thing here. All right, I mean, there's nothing I can reduce. I can't rationalize the denominator. So instead, I'm going to rationalize the numerator by multiplying by root x plus 2. And they do indeed match. So which one's better? I don't really know. It's up to you. I would be prepared to show your work using both methods. Since we're here, let's actually find the equation of the tangent line, and let's find the equation of the normal line. So we know that the slope is 1/4. The perpendicular slope is -4. And remember, that's the normal line. Oops. Okay, and at x equals 4 or a equals 4, whatever. So that's the point 4, 2, which we did right here, right? I gave you that a was 4, x was 4, and you plugged in, you evaluated the function at 4, and you got 2. So now you have a point, you have a slope, whichever. I'm going to do point slope form. I always do point slope form. This is the equation of the tangent line, and the normal line will be y minus 2 equals -4, x minus 4. Take a minute, plug all of that into your calculator. When you graph any kind of tangent line on your calculator, let me turn off this one. When you graph a tangent line on your calculator, it always looks like it's intersecting the curve at several points. But if you zoom in, you will see that it's clearly only intersecting the curve at one point. Speaking of graphing, you can graph the derivative slope of tangent lines. So we're going to take a look at one of those. Okay, so let's look at the graph of, let's just do, doesn't have to be perfect. I think there's a graph of this in your book, perhaps. I'm not sure what number. So this is my curve. Remember, the derivative is the slope of the tangent line at any point. This curve is continuous, so it has a derivative all along itself, let's say. Let's start here. And remember, my graph obviously is not drawn to scale. It's not perfect. Those 2 points. It looks like a weird smiley face. The tangent right here is horizontal. So the slope of the tangent is 0. And same thing here. Slope of the tangent is 0. From this point, positive values of x past this point, I'm using my ruler to demonstrate the tangent. The tangent is positive, positive, and it's getting steeper and steeper and steeper and steeper. So here on out, the slope is positive and increasing. And the same can be true in the opposite direction. So for negative values of x, past whatever value of x this is, as you're going left, as you're approaching negative infinity, the slope of the tangent lines are becoming increasingly and increasingly and increasingly more negative. So m is negative, and we're going to say, and how about its absolute value is increasing. It's becoming a greater negative number. All right, so what's happening between the value of x right here and the value of x right here? Okay. From this negative value of x, let's just call it, let's call it negative a and positive a. It's supposed to be a symmetric graph. Of course, we know my graphs never look symmetric. So assuming this graph is symmetric, we have a value negative a and a value positive a. What's happening to the slopes of those tangent lines? Okay, so from negative a to x is 0. Tangent line is positive, 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 positive. So between, let's use a different color here. Here to here, the slope is positive and increasing. And between 0 and the positive value of a on my graph, the slope is, let's do it this way, negative, 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 and approaching 0. So here, m is negative and approaching 0. So here it's 0, it's positive and increasing. Here it is negative and approaching 0. We can graph that. I'm going to use the same values of x, but now we're going to talk about the derivative. So we're going to graph the values of the slope onto this axis. All right, so remember I talked about some value a and some value negative a. So here is negative a and here is positive a, whatever. If it helps you, like create some actual points to graph, that might be useful. At negative a, the slope was 0. So at negative a, my slope was 0. And at positive a, my slope was 0. The video glitched. I have no idea where I left off. negative a, positive a, and 0. We said the slope was 0. Negative a, positive a, 0. So remember, this represents my x values. X was negative a, the slope was 0. X was positive a, the slope was 0. We said that to the values to the left of a, to the value left of negative a, it was negative. So it's negative, slope is negative, and it's increasing till it hit 0. Positive a to the right, positive a to the right. We said it was positive and increasing. So the slope is positive and increasing. Between's a little funky. We said from negative a to 0, this section right here, it was positive increasing. It has to come back down to 0. And then we said it was negative and approaching 0. How far down does it go? Doesn't matter. We will do much more graphing of derivatives in the next few lessons.